Hi Rock Buds, it's Rock Papa. Hope you guys are surviving Hurricane Helene and come out okay. We're going to focus today on Zion National Park, one of the beautiful places of the West. We'll get kind of oriented to the park, what's where, and then we will look at how the rocks of Zion National Park formed one layer at a time. Look at some pictures of these rocks, and we'll kind of learn how to identify where you are and what rock strata you're looking at when you're in Zion hiking or just driving through. So hope you like this video. If so and it's useful, please subscribe. Thank you so much to my wonderful subscribers. You guys are A-OK. You're number one with me. So here we go, Zion National Park, Geology. As usual, let's start out with the Zion National Park slideshow. Zion National Park is located in the southwest corner of the beautiful state of Utah. Just a little bit northeast of St. George, Utah. You can see on this map that Zion has two parts. The lower part is the Zion Canyon itself. Zion Canyon itself is about 15 miles long and maybe a mile plus or minus wide. The entire park covers about 230 square miles, with elevations ranging from about 3,500 feet in the valley up to almost 9,000 feet in the surrounding heights, and those figures are feet above sea level. The beautiful Virgin River, a major southwestern Utah river, flows through Zion Valley and has done the work of carving out the valley from the surrounding rocks. The northwest portion of Zion National Park is called the Kolob Canyon section. It has far less visitation than the Zion Valley itself. To get to it, you just go up north on Interstate 15 and you'll come to an exit on the right that will take you to the Kolob Canyons Visitor Center and all the beautiful trails up there. Okay, let's get into Zion geology. But wait, this is not Zion, this is the Grand Canyon, the rock strata of the Grand Canyon. I put this up here to show you that the very top layer of the Grand Canyon is called the Kaibab limestone, and we're going to see something interesting about that in just a minute. Here is the Kaibab limestone in the Grand Canyon that forms the most upper layer of the Grand Canyon. Here's one of the roads on the north rim of the Grand Canyon, and you're looking at Kaibab limestone. Kaibab limestone is very siliceous. That means it's got a lot of quartz and a lot of chert in it. And Grammy and I rode 45 miles on these roads when we were over there, and we got 2 punctures because the tread on our tires was a little bit low. So if you go there, beware. Now we're looking at the rock layers of Zion National Park. And what rock layer do you see on the very bottom of the layers of Zion? Now I presume that the layers above the Kaibab limestone also used to exist at the Grand Canyon, but uplift and erosion has worn them away. At Zion National Park, the Kaibab Formation is not really very visible because it's covered over by so much other stuff. But you can see some of it in the Kolob Canyon section of the park. We're now looking at 270 million years ago. This is the late Permian time, and the star on the map shows you where Zion National Park is. This is the Kaibab Sea, a shallow, warm sea that formed, and geologists tell us that the Kaibab was the very last passive margin that formed on the west coast for a long, long time. In other words, lots of tectonic crashing and smashing was coming in from the west that would transform this passive margin into the mountains and deserts of the Triassic and Jurassic periods. During the very beginning of the Triassic period, about 250 million years ago, the Great Dying occurred. That's the Permian-Triassic extinction event. 95% of Earth life perished during this cataclysmic and toxic time, and the Zion area was raised up above sea level, doing away with the Kaibab Sea. The Great Dying happened because supercontinent Pangaea was just beginning to try to break apart, and way off in Siberia, massive amounts of basalt lava erupted for hundreds of thousands of years, belching huge volumes of poisonous gas into the atmosphere that poisoned the earth and the sea. Then, in early Triassic time, about 245 million years ago, the Sonoma orogeny occurred, and its foreland basin created the Sinbad Sea just about where the Kaibab Sea had been. The Sinbad Sea, which was composed of mud and limey mud and other materials, was the very first formation of the Triassic Moenkopi Formation. Then, from both the west and the east, repeating layers of chocolate brown sand and mud accumulated on the edge of the Sinbad Sea, and this dark chocolatey brown material is characteristic of the Triassic Moenkopi Formation. Petrified ripple marks are a huge part of the Moenkopi Formation. Here the red arrow shows you how the tidal currents were flowing. This interesting rock used to be mud that was dried and cracked and shrank, and then some other material filled in the cracks. Another feature of the Moenkopi Formation. In Zion, you can find some Moenkopi at the entrance to the Kolob Canyon's Scenic Drive. Hey, Rock Buds, you know I said that Moenkopi deposits came from both the west, which would be the Sonoma Mountains eroding, and the east. So let's take a look at the east side, what was going on, how much sediment was coming down, and why. By Triassic time, the eastern part of the continent had received 3 major mountain building events, and it was the high ground of the whole continent. The western side of the continent was an immense, relatively flat coastal plain that was just above sea level. So that throughout the entire Triassic period and most of the Jurassic period, material was eroding from these eastern mountains and slowly but surely making its way to the west coast, including the location where Zion National Park is today. All of this material eroding from the ancient Appalachian Mountains not only deposited the Moenkopi Formation of Triassic, but also the Triassic Chinle Formation about 220 million years ago. The first of the Chinle deposits is the Shinnerup conglomerate, which is made of smooth round pebbles embedded in a finer matrix and deposited by fast-moving rivers. This is because for some reason the erosion gradient had been increased. In other words, the land had been raised up so that the rivers that formerly had only the strength enough to transport the silts and muds of the Moenkopi Formation now had the power to transport the pebbles of the conglomerate. One possible reason for this rise in land and increase in the erosion gradient could be the Nevada Neurogeny 4 bulge, which was probably in that area about this time. Here are the best Shinnerup conglomerate pictures that I could find. And one lucky thing about this is that if you can find this conglomerate in the rock stack, you know you're looking at the beginning of the Chinle Formation. The next deposit of the Chinle Formation was the Petrified Forest member, which includes the Painted Desert rocks. These are mainly mudstones that were deposited in a low gradient river environment. Hey guys, so what's the difference between mudstone and shale? Well, mudstone is made of only clay mineral particles, and it can be big and blocky, not thin in plates like shale. Also, shale can be composed of clay particles, quartz, iron, and even feldspar particles. Shale is more of a mix, and it becomes kind of thin and easily split. So where did all these crazy colors come from that we find in the Petrified Forest and the Painted Desert? Once again, we go back to the Nevada Neurogeny volcanoes. They were exhaling tons of volcanic ash that had all kind of stuff in it that imparted these colors to this material. You may come across some of this weird clay that looks like popcorn amongst these deposits, and it is called bentonite clay, and it formed from very fine volcanic ash. Hey guys, before we go on to the Jurassic period, let's kind of summarize the Triassic, because this can get complicated. We just got two formations to deal with. The very first or oldest is the Moenkopi Formation, and it's just chocolatey red mud. Then on top of the Moenkopi, we have the Chinle Formation about 220 million years ago. The first deposit was the Shinnerup conglomerate that marks the beginning of the Chinle, and above that is the Petrified Forest, Painted Desert, and you know what those look like. Now we're going to get into the rocks that really define the walls of Zion Canyon and give it its scenic beauty. These are rocks deposited during the Jurassic period, which lasted from about 200 million years ago to about 150 million years ago. The first deposit of the Jurassic period was the Moenkopi Formation, which is a slope-forming deposit that has a lot of mudstone in it. The Moenkopi mudstones and the Wingate sandstone to the east are really part of the same deposition cycle. The rivers that were flowing into that area could bring down the sand for the Wingate sandstone only so far, and the winds began to blow it up into dunes. But these rivers could carry the mudstone of the Moenkopi a little farther to the west to cover the area that's Zion today. Here's what the Moenkopi Formation looks like, and it's pretty visible throughout most of Zion Canyon. After a while, the sands that created the Wingate sandstone finally made it to the area of Zion in the form of the Springdale Sandstone Formation. The Springdale Sandstone is a prominent feature of Zion Canyon. It's a cliff former, and so you can usually easily find it, and that helps you locate the strata that are below and above it. Springdale sandstone is the second biggest cliff former in Zion, with the Navajo sandstone being the biggest, of course, by far. In this picture, the Springdale sandstone is easily spotted, and so we know the Moenavi Formation is just below it, and just above it is the Kayenta Formation, the next formation we're going to look at. The Kayenta Formation was deposited around 180 million years ago, and it is a slope-forming deposit. It's made mostly of sand, mudstone, and siltstone that was deposited by rivers that were flowing through very hot, dry lands. I think, technically speaking, the Springdale sandstone is considered part of the Kayenta Formation, but it messes with my mind to think of it there. It helps me to think of it as the next step after the Moenavi Formation. So do it either way that helps you, and take it with a grain of sand. Next in line, we have the massive Navajo Sandstone Formation, a major cliffed. Shucks, I keep saying cliffed. I think because my grandsons say it that way. A major cliff-forming sandstone that without which the Zion Canyon would not be the Zion Canyon. Let's have a look. The Navajo sandstone represents the greatest sand dune desert that ever existed on Earth. The Navajo sandstone sticks up about 1,000 feet from its base to its top, and a bunch of it has already been eroded away, so it must have been massive in the beginning. The Navajo Sandstone Formation is whitish at the top, kind of pinkish below that, and reddish, dark reddish at the bottom. Originally, it was all dark red because of the iron in it. It was deposited in an extremely hot, very dry environment, and the iron in the sand oxidized to red. Then, about 170 million years ago, the Nevada orogeny foreland basin, which is called the Sundance Sea, was, believe it or not, deposited on top of the Navajo sandstone, and groundwater from that sea and other sources bleached out the upper layers to white and the middle layers to pink. During Navajo time, plate tectonics had shifted this area so that the wind was now blowing from the west, and so the west wind blew all this sand into sand dunes, massive sand dunes in this hot, dry climate. The Temple Cap Formation tops off the Navajo sandstone, but only in a few places, and the Temple Cap Formation is only preserved at Zion National Park. It is made of sandstone and mudstone deposited on the very edge of what I believe to be the very beginning of the Nevada orogeny foreland basin. So guys, let's look at some rock layers of Zion and see if we can figure out what we're looking at to get a handle on identifying these rock layers in this wonderful place. Looking above the visitor center, we can easily identify the Springdale sandstone. So we know it was Jurassic, and below it is the Moenavi Formation, which was the beginning of Jurassic, and above the Springdale sandstone is the Kayenta Formation. And on the very tippy top, we can see the Navajo sandstone. Once again, we can easily identify the Springdale sandstone, the second biggest cliff-forming deposit in the valley, and so we know that the Moenavi Formation is under it, and the Kayenta Formation above it. Here we have the Navajo on top, so we know Kayenta is under it, and we can easily see the Springdale sandstone that's under Kayenta, and we know that the Moenavi is right below Springdale. This one is easy, right? And you will notice that the Kayenta Formation has a little cliff-forming sandstone strata in its middle. This one is a little bit tricky because you can see that cliff former of the Kayenta Formation forms a kind of a flatland before you get to the Navajo sandstone. And the Springdale sandstone, which is below the Kayenta, is not very tall in this picture. Here's a kind of tricky one. The striped strata in front of us must be the Chinle Formation of the late Triassic, and so maybe that flat base below it could possibly be the Shinnerup conglomerate, which is the beginning of the Triassic Chinle Formation. Now let's go from the top down. In the very back of the picture, I can see the reddish sandstone of what I believe is the Temple Cap Formation. Below that is the whitish sandstone of the Navajo sandstone. I can't see the Kayenta Formation, but I think I see the red sandstone of the Springdale sandstone about mid-picture. Meaning that top cliff former on the right is a continuation of the Springdale sandstone, then I know that slope former below it must be the Moenavi Formation. Here's a really great picture, so see if you can work out what's what here. Okay, Rock Buds, that's it for Zion National Park. Thank you so much for watching. I hope this video was useful. If so, please subscribe. And this is your Rock Papa saying happy rock hunting to all my wonderful rock buddies. Papa out.